my name is Daniel Sun, and today I'll be talking about Leslie population models and predator prey and competitive populations. His work was done in Small Math Research 2024 with my co-authors Pico, Saad, Janine, and Professor Miller. Okay, before I move on to talk about Leslie matrix population models, let me talk a little bit about the classical Lockton-Volterra model. Lockton-Volterra models model predator-prey populations using continuous prey and predator densities. So X and Y are both prey and predator densities, and R reproductive rates and A predation rates. And once this system of linear equations are established, it is not hard to show through ODE methods that if R minus alpha beta is greater than zero, then the system converges to a positive stable state. Okay, so this is a nice result. However, we must assume that the predator and prey populations are homogeneous. However, this is not necessarily realistic because we expect that the fertility rates and the predation rate decreases as the population ages. So, in order to account for more realistic cases, we introduce age group structure. Equation 3 describes a single species model where there are n different age groups. After each discrete time step, the age group ages by like 1 unit, and also reproduces itself by a fertility rate small f, which is greater than zero. Okay, so let's consider a explicit example of a predator-prey model that is determined by a set of Leslie matrix equations. So suppose we have whales and planktons, and suppose the whales are comprised of three different age groups, AN of 1, AN of 2, and AN of 3. And so assume that they grow on plankton, which is described by quantity Bn. And we set our population vector Pn to be An of 1, An of 2, An of 3, and Bn. Then we set the dynamics according to equation 4. Here, small f is the fertility rate of the whales, large F the fertility rate of plankton, M the growth boost that comes from predation, and K the predation rate. Now we notice that if the predation is high, the preys are completely exhausted, and if the preys are exhausted, the predators will also be left to decay to zero. However, if the predation rate is small enough, it is possible to attain mutual population growth. Okay, so let's generalize this simple example into a more general case. So, for simplicity, assume that there are same number of predators and predator age groups and prey age groups, and we describe the population vectors by alpha of small n and beta of small n, both with dimensions 1 times large n, and we set the dynamics according to equation 5 and 6. So the predator population is described by its inherent growth by Leslie matrix LA, plus the boost that comes from predation, which is Km times beta of n. The prey population is described by its inherent growth rate LB beta of n minus the predation K times alpha of n. Here, K is a predation ratio, M is a nurturing ratio, and both ratios are assumed to be positive. LA is the Leslie matrix of the predators, and we assume that the dominant eigenvalue, or the eigenvalue with the largest modulus, is less than 1. And LB, the dominant eigenvalue of the Leslie matrix, the Leslie matrix of the preys have a dominant eigenvalue greater than 1, i.e., in time, the preys are expected to grow. Okay, so again, as in the first example, if consumption is too high, both populations die out. However, if consumptions happen only in small amount, it is possible to attain exponential growth for both the predator and the prey. Now, our goal is to find a necessary and sufficient condition for the predation rate K to guarantee mutual population growth. And in order to attain this, we need to solve for the system of recursive equations in 6 and 7. And it is possible to recast the coupled equation into a single second-order recurrence relation, as described in 7. Now, since LA and LB are matrices, they're hard to deal with, so we consider the most simple case when the dimension or the number of age groups are equal to 1. So we set large L of A to be some scalar small L of A less than 1, and large L of B equals small L of B, which is greater than 1. And it is not hard to use the method of companion matrices to show that neither population vanishes in the infinite time limit if predation rate k is less than or equal to square root of 1 minus LB times LA minus 1 divided by m. Okay, but what about the general case when the number of age groups large n is greater than 1? We were able to address this case for one particular case where the Lessing matrix of the predator is a scalar multiple of the Lessing matrix of the prey. And in these cases, we notice that the predator population alpha of n is described by growth matrices lambda 1 and large lambda of 1 and large lambda of 2 that are defined in terms of LA and LB. B1 and B2 are some initial population vectors. Now, the dominant eigenvalue of lambda 1 and lambda 2 are bounded over by the quantity in 11. So basically, what we're saying is that the growth rate of the prey of the predator is described by this quantity in 11, and likewise, because the coupled equation displays similar behavior, we can say that the similar growth rate bound applies for the predators. However, the case when LA and LB do not commute remains as an open question. Okay, so now let's talk about the competitive model. In the initial case, we assume that predation increases the population of the predators, but decrease the population of the prey. However, in the competitive model, interaction reduces the population of both species. Now, instead of considering different species, assume that in this case we have a single species system that is characterized by two different groups of different comparative advantages. Because all the populations within the system are assumed to come from the same species, we set a same growth matrix, L equals to large L of F, and we set the population dynamics according to 12 and 13. We can ignore the max function because it basically guarantees that each of the population are non-negative. And we set alpha of n plus 1 equals to Lessing matrix times alpha of n minus kn beta of n, i.e. The competition decreases the population group alpha, and beta of n plus 1 equals to L beta of n minus K alpha of n. Now notice that the competitive advantage ratio M describes which group has more advantages. So, like for example, if M was chosen to be 1/2, then upon same interaction, the population decay of alpha would be less than the population decay in beta. So therefore, in these cases, if given the same initial population vectors, alpha has competitive advantage. Now, theorem 4.2, the last species standing theorem, prescribes exactly which population dominates in the time n goes to infinity limit. If we assume that both population groups are homogeneous, i.e., there are same number of same number of population among each age groups for both group alpha and group beta, then we can set large D equals to alpha naught minus square root of beta naught, which is a single real value parameter. Depending on the sign of D, we can find out which population, either or alpha or beta, wins in the n goes to infinity limit. If D is positive, then alpha goes to infinity and beta vanishes to 0. If D is less than 0, alpha vanishes and beta grows. If D is exactly 0, both populations vanish or both grow at the same time. And the approach to prove the theorem is basically to reduce down to eigenvalues and use a modulus as time small n goes to infinity. Okay, so we wish to apply this results on competitive populations in a realistic example. Parnasium aurelia and Parnasium cadentum is a good example to do this. These two organisms are Parnasiums that individually, in the absence of one another, display logistical growth. So it must be noticed that Parnasium aurelia has competitive advantage over Parnasium cadentum. So in case where the population reaches equilibrium, there will be more Parnasium aurelia compared to Parnasium cadentum. Now, our goal is to fit the population data of P. aurelia and Parnasium cadentum to the competitive model and find the underlying parameters. Now, there must be two things. There must be two milestones that must be addressed in order to achieve this goal. First one is how do we quantify the goodness of fit, and secondly, how do we tweak the parameters to minimize this error rate or maximize the fit. We define the error of the fit by the parameters fk, beta naught, and m. And basically, these four parameters of the population model would give data points, and we basically apply the same chi-square definition in order to quantify the fit. However, the usual method of linear recursion would not work because our model is recursive, and therefore we apply a machine learning scheme or basically a gradient descent on each parameters to minimize error. And once doing this fit, we obtain a value of chi equals 3.11 for 20 data points. And notice that though there are 20 times 2, so like 20 days, 20 data points times two different age groups, so there are 40 degrees of freedom. We snip out the last 20 because our model does not account for stability. And this 3.11 rate is less than 10.351, which is a 5% confidence interval threshold for 20 degrees of freedom. So we can say that our model is correct up to a 5% confidence interval. Okay, here are some open problems. The first problem is, can we provide a sufficient condition for the population growth of predator-prey model where LA and LB do not commute, which was the case that cannot be addressed using regular eigenvalue methods or quadratic equation methods that we used in the first section. Now, the second open question is it possible to create a Leslie matrix model that displays saturation or logistic growth? If this can be done, we can obtain a better fit for the example of Parnasium aurelia and Parnasium caudatum. The last one is to formulate a Leslie population model for open systems with migration. Now, thank you for listening, and I will take questions from the audience.